Welcome to Chapter 7. Now we shall learn how to calculate the pH of buffer solutions using Henderson-Hasselbach equation before and after the addition of strong acid or strong base. Now let's look at how to calculate. Okay, this one is calculates the pH of a buffer solution containing 0.1 molar of ethanoic acid. Okay, CH3COOH, we know that it is a weak acid solution and 0.02 molar of sodium ethanoate. Okay, sodium ethanoate, we know that it is a salt. Okay, then given Ka. Now, in this solution, if we want to find the pH, it's easy because it's mentioned buffer solution. So buffer solution means we have to use Henderson-Hasselbach equation. Okay, for Henderson-Hasselbach equation, must remember it is conjugate base over weak acid. Now, how to substitute the information into the Henderson-Hasselbach equation? Okay, now we have weak acid 0.1 molar. So this one is 0.1. Okay, this is easy. Now, how do we get the conjugate base concentration? Okay, we know that if weak acid, it dissociates little only. So the concentration of CH3COO minus is actually very little if comes from weak acid. Thus, in the buffer solution, just now we mentioned that CH3COONA is a salt. So salt completely dissociate. So when salts completely dissociate, what happens is it will become CH3COO minus aqueous plus Na plus aqueous. Okay, so if this one, if CH3COONA is 0.02 molar, when completely dissociate, we will also get 0.02 molar. Thus, we are going to get conjugate base is actually comes from the complete dissociation of salt. So it's 0.02. Okay, so the final answer, we will get 4.05. Okay, how about basic buffer solution? Okay, it is the same. Okay, so first of all, okay, when we look at it is a NH2 and it's given Kb means it's a weak base. Okay, weak base, and then let's look at this. Okay, this is the salt. Okay, this is the salt. Okay, and then it's given Kb. Now, so for Henderson-Hasselbach equation, for basic buffer solution, we will use conjugate acid over weak base. Okay, now let's see what do we have. Okay, we have weak base information 0.3. Okay, same thing as well. Because this is a weak base, so if weak base dissociate, we only have very little of conjugate acid ion. Okay, so where do we take the concentration from? We take from the salt because the salt will completely dissociate. Okay, so if we will get C2H5, NH3 plus, and Cl minus ion. Okay, because salts completely dissociate, so 0.5 molar completely dissociate, we will also get 0.5 molar of C2H5 NH3 positive ion, which is the conjugate acid. So substitute 0.50 inside. Okay, so this one comes from the salt. Okay, then you get POH, not pH yet. After that, you can find pH by 14 minus POH. Okay, now let's continue to another one. Another one is a little bit special, that is addition of strong base and then addition of strong acid. Okay, so how do we do first? Okay, let's look at the question. The first one is calculate the pH of the buffer solution. It didn't mention anything about adding strong acid or strong base yet. Okay, so let's start. Okay, same thing. This is a weak acid. So we use conjugate base over weak acid. Okay, you can notice here why here did I put volume. I put V. I didn't put 500 ml because remember they are in the same solution. Okay, they are in the same solution. CH3COO minus and CH3COOH, they are in the same solution. So if this is 500 ml, so both will have the same volume. So I just use number of mole because volume can be cancelled out. Okay, so finally I will get 4.88. Okay, this is the pH before strong base or strong acid is added. Okay, remember if it's a buffer solution, it only tolerates small amount of strong acid or strong base. Okay, now let's go to part 1 where we have addition of strong base. Okay, strong base we have 0.02. Okay, so it is addition of strong base. Okay, see why do I change to mole? Okay, I change to mole because in this question, it never mentioned about the volume of potassium hydroxide. Is it 1 decimeter cube? Is it 1 centimeter cube? Okay, or is it 5 centimeter cube? It never mentioned. Okay, but we do know that they will be in the same volume. Okay, meaning that if I add in strong acid or if I add in strong base, the volume might increase. Okay, but they will still have the same volume. So we can cancel out in the solution, the calculation. Okay, so what happened here is we calculate the mole of strong base. Okay, just remember something. In the buffer solution, in the buffer solution, we have CH3COOH and CH3COO minus. Okay, this is weak acid. This is conjugate base. So if you add base, means base will react with acid. Okay, so we come up with this equation. Okay, and then single arrow because we have strong base. So strong base will completely react because it is a small amount. So it is like limiting. It is behaving like a limiting reactant. Okay, so after you solve the ice table, you will get the number of mole for conjugate base after adding small amount of OH, and you will also get the amount of weak acid, okay, after adding small amount of strong base. Okay, after you get these two concentration, what you do is again substitute into the Henderson Hasselbach equation because this is still a buffer solution because only added small amounts of strong acid or strong base. So the pH will be maintained or almost the same. Okay, after calculation, you can see it is 4.86. Okay, after addition of strong base. Before the addition of strong base, we have 4.88. So the difference is not big. So means that the buffer solution can maintain its pH. Okay, just now we add strong base. Okay, now we add strong small amounts of strong acid. Okay, same thing again. In the buffer solution, we have weak acid and also conjugate base. Okay, if we add strong acid, so means acid will react with base. Okay, so now, and then remember, strong acid completely dissociate. Okay, so strong acid, because it is only small amount added, so it is the limiting reactant. It will completely consume. Okay, so same thing, we will still get conjugate base and also weak acid mole. Okay, we do not use concentration because the volume is the same. Okay, so substitute again in the same thing, that is the Henderson Hasselbach equation. Then you will get the final answer pH. Okay, and you can see the final answer is 4.87. So just now, before addition of strong acid or strong base, just a buffer solution, we got 4.88, meaning that after the addition of strong acid, small amount of strong acid or strong base, the pH of the buffer solution maintains. Okay, so this kind of question is very easy to do. Okay, just remember, if this is an acidic buffer solution, if this is a base acidic buffer solution, then we will have weak acid and conjugate base. If you add strong acid will react with conjugate base. If you add strong base, it will react with weak acid. And remember the ice table. The amount of strong acid or strong base added will be the limiting reactant. It will be completely consumed. Okay, so remember, just easy. If it's just a buffer solution without addition of strong acid and strong base, just use Henderson Hasselbach equation. If there is addition of strong acid or small amount of strong acid or strong base, use ice table. Okay, and then again, same thing, substitute into the Henderson Hasselbach equation. Okay, that's all for how to calculate the pH of a buffer solution using Henderson Hasselbach equation before and after addition of strong acid or strong base.